Hi, this is Robert Bolaños. Welcome to the analysis and design of a flyback. This is video 34. Hopefully this will be a short video. What is reverse recovery of a diode? That's a very important subject. That's something that I learned at a very young age when I was a interior repairman back in the 1970s and 80s. Television started using switch mode power supplies, and a lot of the times the diodes would fail. They would fail short, and at that time uh, we would replace them with regular diode, regular 60 hertz diodes, and would put them in the switching power supply, and the diodes would heat up, or the power supply would heat up and short the diode again. And at the time I was a fairly young man. I didn't know the difference between a fast diode and a slow diode, and putting a slow diode in place of a to replace a fast diode didn't do didn't work. So that's an important subject. So what is the difference between the fast and slow diode? So we're going to cover a little bit of that. And then, are they interchangeable? Okay, so I'm going to go ahead and give the answer right now. In most cases they are not, and I'll say not interchangeable if you're using them in switching power supplies. Okay, switching power supplies, which is the subject of this channel. Okay, now the example that I'm going to be using for a slow is the 1N4004 diode. Okay, and let's go ahead and see if I can explain what this reverse recovery is. So if you have a circuit like this, and this is the physical interpretation of your diode, and let's say you have a power supply or a function generator, we can say, and let's say we're switching from 0 to, let's say, 10 volts, and then let's say we connect this through a resistor to limit the current. I think the resistor that I'm using is 500. Okay, so let's do that. 500 ohms. Okay, well, when you're at 0 volts, there's no electrical potential, so the diode is off. Okay, so VN diode is off. Okay, but then as soon as you switch to a high, you're going to have 10 volts here, and then because of the diode drop, you're going to have 9.3 volts here, and of course you're going to have current going through that. So okay, so what happens is the harder you draw, or the more current, you get a little depleting layer. Let me go ahead and make this red. It's a storage device. This is a storage time, and it basically, you get a charge built in here on the depletion layer. Okay, and then when it goes back to 0, Okay, so this is 0. Then theoretically, and let me backtrack a little bit. So when you were at 10 volts, the diode is on. Okay, but now we're going from this transition from 10 to 0. So we're going to say 10 to 0 volts. And the condition of the diode, when it reaches 0, should be off. But in this case, it's not off. It's actually still turned on. Okay, it doesn't turn off, especially if it's a slow diode. Okay, so let's see what's happened when this goes to 0. So you can think of this as a short. Okay, but there's a storage charge, a stored charge. That acts like a little battery, basically. You can think, at least that's the way I envision it, like a little charged battery. And let's say it's a charge of about a diode. All right. So remember, if you have a charge built in, current actually prior, when this was on, the current was going in this direction. When this was at 10 volts, it's going in that direction. But now that this is turned off, the 10 volts is turned off, and now you have a charge. Well, the charge of this, of a positive device, is going to go out the positive. So now you're flowing in the opposite direction. Okay? I hope you got that. Okay? So let me do that. That when this positive is on, current I, and I'll say I on. Okay? And then when it goes back to 0, there's an I off. You could think of it in that direction. Okay? So until the charge in the junction dissipates or discharges. Okay, so that's the important fact, and that's something that we need to understand. So in this case, the diode is going to be on, and that's because you have a slow diode. Okay, and this is an example of, let's say, a 1N4004. So let's go ahead and see if we can go to the SPICE simulator. Okay, and let's see if we can see some of that charging effect. And what I want to do is I want to go ahead and I'm going to model a slow diode, and then I'm going to model a switching diode, which is a 4144. Okay, so now I want to go ahead, I'm going to comment this, which is the voltage across this diode, the fast one. I just want to look at the voltage across VO1, which is the 4404. So I'll put a little comment there, a star. Oh, good. Okay, well, that did it. Okay, so we'll go to home. That's what I forgot to do. Okay, so now I am putting a pulse here, and it's 5 volts, and I got a time delay in the fast. Rise time is 1 nanosecond, 1 nanosecond. Pulse width 5 microseconds. That's a pulse width. And here's the T period. T period, I define it as 10 microseconds, which is 50% duty cycle. Excuse me. So I'll go ahead and press run. And here is the current. Okay, so this is the current of the diode itself. Okay, so if you notice, let me go backtrack. Let me do this. Let me put signal here, and I'm going to comment this out because I want to show that the current is actually there and dissipates. Okay, it's like G. So bear with me. Okay, and what I'm going to do is I'm going to change this 10 times bigger. Okay, so you can actually see the charge time. Okay, there. Okay, here is the current through that diode. So, and I'm not displaying the signal. Why not? Oh, okay. Let's go ahead and do that. Okay, so here we go. So here's the voltage in, goes to 10 volts. Okay, so then the current follows. Okay, so then this current should be approximately 10. It should be 10 minus 1 diode drop divided by that current, which is approximately about 18, 19, 18.6 milliamps. Okay, which makes sense. Okay, so let's see if okay, so it's basically 9.3 divided by 500, about 18, 18.6, 18.6. Okay, makes sense. Okay, so now I mentioned that when it goes from 10 to 0, that the diode is still on. Okay, that's what I mentioned, that it's still on, and that you're going to have reverse current. Okay, so let's look at this. So now if you notice, this is positive current, this is forward current, but then when you go from 10 to 0, you got a negative current. In other words, it's flowing backwards. See right there? It's negative. Okay, and as a matter of fact, it's negative 1.3 milliamps. Okay, so in that case, that's because this is what's happening. So now, since this is short, so the current ID during the transition off is going to be approximately 0.7 divided by 500. Okay, so 0.7 divided by 500. No, 500. So it's approximately 1.4, and let's see if that is the case. 1.4, and it says 1.3. So 1.4, 1.3, that's close enough. And if you notice, then it decays, and it goes back to 0. Okay. So now let's plot what a fast diode does. And this would be the 1N4144. Okay, let's go ahead and move the ID to this. Oh, sorry guys, having a little senior moment with all these little errors. Okay, and let's see if I have it in display. Okay, so now this, I'm gonna go ahead and label this. This is the current on the 1N4004. This is the 1N4148. Okay, and if you notice, see, it looks like it doesn't have the reverse recovery. Okay, it goes 0, goes up to about 18, and then it goes down, and then it doesn't have this storage time. But in reality, it does have. You notice right there, there's a little tip there. Okay, a little tip. So if we go in there, see that? See that, my friends? You have a little bit of recovery, but it's much shorter time. Let's see what the time is on that. Okay, so the reverse, let's go from here to here. It's a lot shorter. It's only 35 nanoseconds. Okay, let's measure the time. So this is, go ahead, put 35 nanoseconds on this one, 35 nanoseconds. Okay, and then for the 34, we'll measure from here to here. You're talking about 13. That's a huge difference. Okay, huge difference. Okay, so let's see if we can add, let's see, about 13 microseconds. Okay, so in this case, if you have anything that is switching, let's say you have a time constant, or let's say you're switching power supply, is you're switching at 100 kilohertz. Well, the time period of that is 10 microseconds. Well, this is longer than 10 microseconds. So that means that if you use this in a power supply, it's going to conduct, but then during the time period, you always will have current going the opposite way. Okay, so let's see what happens. Let's do that. Let's go back. This would correspond to a switching power supply switching at 100 kilohertz. Okay, the period would be 10 microseconds. Okay, see what happens? Okay, so now it's switching. Let's go ahead and change this other one. This one we'll cut and we'll put it in the. Okay, so if you notice here, this is a the 1N4004. It conducts, and then throughout the entire switching time or period, it's conducting the opposite. It never goes to 0. So what happens if you use this in a switching power supply? Your capacitor will never charge, because it'll be charging and then it'll be discharging. Okay. Now look at this here. See, you have the little tip right there. So it eventually is only reverse current of very short time. In this case, it was like 35 nanoseconds. Okay. So now let's change this to a 1N, which is a Schottky, a 5822 diode. I believe they have extremely low or no charge or storage charge or reverse recovery. Let's see if this models that. And let me go ahead and put this at we'll put that at 3. Okay, we'll run it, and if you notice, we still have the reverse recovery here, but now the one end 5802. See, it has a even shorter, and if you notice, it didn't. The other one went like this and then like that. This one starts discharging, as a matter of fact, at much even lower, faster time. It doesn't hold it, so it doesn't really have a like a whole charge, so it starts discharging almost immediately. Okay, so this is why Shotkeys are often used, not only because of the reverse recovery is extremely low, or if any, and because they're extremely fast, and of course you have a voltage drop which is a lot smaller. Okay, so let's see if let's try to see if we can find I believe I have a model here. It may be this one. Okay, so I have this one here. I'm using the 1N4404, but let's go ahead and see what happens. Let's use a 5801, 5822. Okay, 5822, and this is fast, and at the same time, this is the model that I use to monitor the power that would be dissipated in the IRF 150. And let's see at the output voltage, see how this supply works, and then we'll monitor the TJ, the junction of the transistor, see if it's getting hot. Here I'm using a board temperature, assuming that the board temperature is 25. And I'm also monitoring the temperature of the junction of the 5822. And what I'm really looking for, I'm really looking for two things, is the voltage output going all the way to 12, and then I'm interested what is the temperature of the junction of the primary transistor. Okay, here we go. Let's see the V out. You notice it goes up and it regulates at 12. So this looks very good. Okay, now here we see the TJ. TJ is the temperature of the primary transistor. It goes up, okay, heats up a little bit, and then it comes down, and then it goes steady state. It's about 30. And then you look at the junction temperature of the diode, okay, and it's at about 25. Okay, so let's go ahead and use a slow diode. Okay, so in the example it's a 4004. Okay, so we'll let it run. Again, we're going to monitor. Almost there. Okay, here we go. So if you notice the voltage, look at that. I can tell you that this is not going to go I can let it run a little bit longer, but it's already going to its asymptote. Okay. And then if you notice, look at the temperature, which is the blue. Okay, the temperature prior was about 30 degrees. Now the junction temperature of the primary is about 60 degrees. Okay. And of course the transistor is about 32. But what you want to do, concern is the temperature in your primary MOSFET has gone up. Okay, so that's because why. The reason is because during the time that these is off and others this is charging, there's current. Basically, the capacitor is prior has been charging, but because the diode does not turn completely off during the recovery, current is going in this direction. Okay, it's going in this direction. It's basically being discharged. Okay. So anyway, that's the difference between using a slow diode and a fast diode. They're not interchangeable in most cases, or certainly the case in a switching power supply. And when you're using, as you go up in faster and faster frequencies or higher frequencies, then you want to be sure that you're using some of the fast diodes or ultra fast diodes, where you have the TRR like somewhere in the 70 nano seconds regions or faster. Anyway, if you have any questions, you can send them to my email of rbola35618 at aol.com, or you can post them here on my YouTube channel, or if you have requests for spice, you can send them or post them here. Please subscribe, share, and give me a likes up if you found this video informative. Thank you for watching.